Thus far, we've been solving problems by writing out this 7-term equation, and we notice that sometimes a lot of these terms actually are zero, and we cross them out of the equation, and the equation gets smaller. I'm going to take a bit of a different approach. Instead of writing all 7 terms to start and then erasing some of them, can I start with no terms and think about what terms should be there? That's a different approach. That might save some writing. It'll also help you, if you're able to do it, it'll help you understand the concepts a bit better. So I'm going to think about that for part A. Determine the speed of the block at point A. So remember, this is frictionless up to point A, so we don't have to deal with friction. So I can ask myself, so the equation usually has two sides, the left side and the right side, with the left side being all the starting mechanical energies. So I can ask myself, what mechanical energy is there that exists at the start? I'll call this the start, moment 1. And at point A, I'll call that moment 2. So what mechanical energies exist at moment 1? I think it's just the spring's potential energy, because it's not moving, it starts at rest, and there's no change in height involved leading up to part A, so I don't even have to deal with the gravitational potential energy. So I think it's only the spring potential energy at the start. And then the right side of the equation is usually all of the mechanical energies at moment 2. So what are the mechanical energies at moment 2 when it gets to point A? Well, I think it's just going to be kinetic energy, because the spring is released at this point, so the spring is not storing any more energy. And like I said, it's not gained any height or anything like that, so there's no gravitational potential energy. So basically, part A is solved with not a 7-term equation, but a 2-term equation. So it's actually quite small. And what's happening is that it's just a simple direct transformation of energy. The elastic potential energy all of it transforms into kinetic energy up until point A. And then I can go from here. So I can write the formulas for each of the energies here. And then I rearrange for the speed. So the 1/2s cancel out. And I'll divide by m and square root. I'll fill in the values. And try to come up with the answer. I don't have my scientific calculator with me, so let's see if this is going to work out. (1600) times 0.14 times 0.14 again, divided by 1/2. And then I've got to square root this. Okay, so it looks like I got a decent answer here of 7.9 meters per second. Okay, so that's part A. Now, how about part B? So for part B, you may think that I'm going to analyze from A to B. However, I am actually going to analyze from the very beginning to B. So I'm going to switch. Moment 1 will stay the same. It'll be when the block is released from rest from the spring. And now I'm going to call moment 2 point B. If you call moment moment 1 point A and moment 2 point B, you're actually going to end up with the same answer. I just prefer using the initial start position. So at this point, what energies are at the start? It's just the spring's potential energy again. However, now the WNC term comes into play, the work done by non-conservative forces, which is usually attached to the left side of the equation. Well, yeah, it is attached to the left side of the equation with the initial mechanical energies. And at moment 2, point B, what energies exist at that moment? Just like part A, it's going to be only kinetic energy. The spring is already unloaded and there's no change in height. So then we follow the same process, but now we have to deal with the work done by friction. So here's the spring potential energy. And now the work done by friction is going to be, I'm going to kind of do it off to the side, I think, just to show you the steps. So the work done by friction will be the force of friction times the displacement from A to B times cosine of theta. So theta for friction is going to be 180 degrees because it's pointing in the exact opposite direction of the displacement. So this will simplify to negative mu times normal times displacement. And in this situation, the normal force is m times g. It's balanced out with gravity. So that's the expression I'm actually going to be putting into these steps here. And then on the other side, it's kinetic energy, so half mv squared. And then we'll plug in the numbers and we'll solve for the speed. So this first term here this is the elastic energy. It's 15.68 joules. And we're going to decrease that by the work done by friction. Which is 3.675 joules. And the other side of the equation, I'll do half times the mass for now. Okay, so we'll go on to solve the rest of it. I won't write down those steps. I'll just calculate it out. Okay, so 6.9 meters per second, which makes sense. We just got it a tad slower than we got in part A, and that's the effect of the friction. For part C, I'm going to erase part A here and use the space for part C. And in this situation, now we're determining the maximum height the block reaches up the track. So I'm actually going to keep moment 1 the same, and moment 2 will be wherever the box reaches some kind of a maximum height here. I'll set my reference height just at the bottom of the track. Okay, so when I analyze the situation, going from moment 1 to moment 2, my work in part B, a lot of it can actually be reused. At moment 1, it's the same. There's the spring potential energy. As it travels to get to the highest point on the ramp, it will have to go through the A to B section. So that work done by friction is still going to be there. So it's a good thing I did not erase that part, because I'll just use those numbers that are right there. And now this time, at moment 2, there's not going to be any kinetic energy when it gets to the highest moment. When it gets to the top, it's going to come to a stop for that moment. So there's no kinetic energy there, but instead, it's all gravitational potential energy. And notice how similar the starting equations are for B and C. Really similar situation there. So on the left side, it's the same as the left side for part B. So I'm going to keep those numbers. That was at the bottom there, 15.68, and then negative 3.675. And on the right side, here's where it gets a little bit different. This is gravitational potential energy now, which is mgh. And I'll solve for h by dividing both sides by mg. So this value here is pretty much 12. I think it's 12.005. Divide that by mg, and that'll get me the final answer. So 2.45 meters, or 2 sig figs, that'll be 2.5 meters.